Hello, and welcome to the AI Research Roundup. I'm your host, Alex. Today is May 5th, 2025. Alright, so we're looking at an interesting ICLR conference paper published just over 3 months ago, back in January, titled Instant Policy, In-Context Imitation Learning via Graph Diffusion. This paper tackles the challenge of teaching robots new tasks quickly, proposing a way for them to learn almost instantly from just one or two examples, without lengthy retraining. Okay, so this first figure really illustrates that core idea. On the left, you see just a couple of demonstrations showing the task. That's the context. Then, in the middle, it visualizes how this context feeds into their instant policy model. This uses that graph diffusion approach, trained on those clever pseudo-demonstrations. And then, boom, on the right, the robot instantly performs the task based just on those initial examples. Building on that idea, this next figure dives deeper into the representation. On the left, we see a local graph for just the robot state and object geometry. But the main part, on the right, shows this novel heterogeneous graph. It cleverly combines the context demonstrations, the current robot state, and crucially, the future actions the model needs to predict. This unified structure is really what allows the diffusion model to work its magic. Okay, so this figure shows how they actually use that graph structure we just saw. On the left, during training, they feed the graph, but with intentionally noisy future actions, into a graph transformer. The goal is to teach the transformer to denoise those actions. Then, on the right, you see the deployment, how the model iteratively refines those noisy action nodes, step by step, until it predicts the final, desired robot action. So, where does the training data actually come from? Well, this next image gives us a look at the pseudo-demonstrations they generate. We see examples of these simulated trajectories for two different pseudo-tasks. It's a really clever approach, generating basically infinite training data procedurally in simulation. This tackles that data scarcity problem head-on and provides the examples needed for the training process we just discussed. Okay, moving to the results. This table really drives home the effectiveness of that pseudo-demonstration training we just talked about. It compares instant policy success rates against several baselines on 24 simulated tasks, split between seen and unseen ones. You can see, especially with added real demos, instant policy achieves really high average scores, 0.97 on seen tasks, and 0.82 on unseen ones, far outperforming the other methods shown here. Okay, so those simulation results were impressive, but how does it hold up in the real world? Well, this table, Table 3, shows exactly that. We see success rates for 16 different real-world tasks, like opening an air fryer or stacking bowls, with 10 attempts each. And again, instant policy knocks it out of the park with an 88.75% average success rate. The baselines are much lower, really showing this approach works beyond just simulation. Alright, so those real-world results really seal the deal. In conclusion, instant policy offers a compelling way for robots to learn incredibly quickly from just one or two demos, a huge leap. The magic really lies in combining that structured graph representation with the diffusion process, fueled by those scalable pseudo-demonstrations. Well, that's our roundup for today. Thanks for joining me, and catch you next time.